Hello, this is the new Class 17 handout. I want to put up this video so both classes have the same information for this first class of new material for Exam 3. And in this video, I want to look at page 4. I didn't get far on allylic halogenation for either class. I want to start fresh with this new handout. I simplified it by removing the BR2 reagent. Allylic halogenation for us is only going to be done with NBS. NBS is N-bromosuccinimide, and the allylic halogenation, you will put a bromine at the allylic position. So we have two allylic positions in this case, one there and one here. The thing is, whether you put the BR at the 12 o'clock position or the 6 o'clock position, you'll get the same product. So I'm going to label these both A. It doesn't matter which one you use. Now, let's make the intermediate radical first. I'm not going to show the mechanism, I'm just showing the intermediate. And the intermediate looks like this. I'm going to make the radical at the 12 o'clock position, but we could also make it at the 6 o'clock position. Now the thing is, you know that allylic radicals, and this is an allylic radical, have resonance. And what color can I use? Let me use purple. And the resonance in this case, you'll have this unpaired electron go there, next door. One electron of the pi bond go there to make a new pi bond. And then the second pi electron goes on that carbon. Thus we have this allylic radical. The double bond shifted, and the carbon that now has the unpaired electron is here. No charge, you know these radicals are neutral. You could always verify with the formal charge equation. Now the thing is, regardless of which radical I use, I will get the same product. So I'm going to only draw it once. And where am I? And I have this. That is an allylic bromide. And if you're not convinced, if I use the second radical, look what I get. I get that. You don't need to know the mechanism, but you should know the radical intermediates. I have that written over here on the right. And since I drew both of these, I need to say that they are identical. A lot of times they're not going to be identical because your two allylic radical resonance structures are different, but in this case, they result in the same product. Okay, so with allylic halogenation, you need NBS and either light or heat. So we have here we have here light. In the next example, we have heat, and go ahead and use my tricks. We have 4 allylic carbons, but again, because of symmetry, no matter where you put the initial radical, these will all result in the same product. Okay. Practice. The more we practice, the faster this will get. Let us draw. And yeah, if it's filling the product, for now, let's go ahead and draw the intermediate radicals. With time, you may be able to take a shortcut and understand that definitely one of the products, you'll have the BR here, for instance. And then in the other product, you would have this shift in a resonance, and this carbon would have the radical. So I did that in my head. Let's do that on paper. Show the shifting of that radical. We have I'm going to use the upper left letter A, and practice. If you need a little more guidance, go to the SI office hours, show them your notes, and they could walk you through it one more time. I'm always double checking as well, right? That my two resonance contributors, they are both allylic radicals. If it's not, then something went wrong in your resonance. And if that's the case, your two products should also be allylic radicals. So here we have this, a little bit neater, Br, plus. Now, again, in the first case, the two allylic bromides were identical. In this case, they are not going to be identical. For sure, they are not identical. Okay. Now, we have to circle the major product. The major product is the more stable alkene. So, more stable alkene is the major product. Do you see how these concepts are coming back? Double bond stability, right? Tetrasubstituted is more stable than trisubstituted, is more stable than disubstituted, is more stable than monosubstituted. We have tetrasubstituted on the left, trisubstituted on the right. This is the major. And so in the second problem, I mentioned there is an issue. The issue is the radical intermediate, the initial radical and the resonance radical give you different products. And then you have to circle the major product if there is a true winner. Now, let me come back to the regioselectivity. The regioselectivity says that in your initial radical, you're making it at the most substituted carbon that has a hydrogen to abstract. So here, secondary beats all these primaries. So that's the winner. Secondary allylic. You want to write that down? We have here secondary allylic. Well, these guys, secondary allylic. Same thing for the first set of radicals. Over here, the last problem on this page, we have two allylic carbons, and yes, they're different now, A and B. But we notice for B, there's no hydrogen. So we cannot put a radical on that quaternary carbon. Quaternary. We do have a secondary here, and that's better than all the primaries, and there is no tertiary. So the intermediate is this. I like to call it the initial, right? The initial allylic radical, right there. The initial allylic radical. Next, we have resonance. I'm not going to worry about the mechanism arrows. You have examples here. It's the one in purple. Okay, the one in those purple fish hooks. Let's practice drawing without the fish hooks. You shift the double bond over. This carbon is now naked, and we have this. Oh boy. You'll see why I said oh boy in just a bit. We have this product. We have Br. Plus we have this product. Br. They are both secondary. Oh no. The double bonds they're both dye substituted. And so I can't really tell the difference in stability. I would predict that these would be, you know what, I take that back. I was going to say they're made in equal amounts. Technically that's true, but that's only because these are identical. You just have to take the one on the left and flip it. Turn it over. Don't rotate it, just turn it over, and you'll get the BR on this side. Everything else is the same. Okay, so these are identical. There is no major because we don't have a mixture. Before I conclude this video, I mentioned again the residual selectivity. That's just saying that you want to make the most stable radical. And then from that and its resonance, you get the two products. And then you have to be aware that if they're identical, you have to say they're identical. If they're not identical, choose a more stable alkene. Now the stereoselectivity is not stereoselective because radicals that carbon is sp2 hybridize, and there's a p orbital, and the bromine can hit the top lobe of the p or the bottom lobe of the p. That could either be top or bottom, or wedge or dash, or front or back. Either way, it's going to be 50-50. Whenever you make a chiral carbon, that bromine will be 50% wedge, 50% dash. If the carbon is chiral, like here and here. Oh no, not here. That carbon is not chiral. I'm not going to make it complicated on the exam. You know, it's not stereoselective, but I will never ask you to draw the stereoisomers of an allylic halogenation. So no wedges and dashes for allylic halogenation. Okay, so that's one good thing. That I remade this handout. And again, the other thing is, we could have done this with BR2 and light. Forget that. In practice, we always use NBS because BR2, sometimes you get dihalogenation, and we want to avoid that. So with NBS, you avoid that. Okay. I'll leave it at that. That is a good study sheet. Introducing allylic halogenation with NBS. On the next video, and the next page, I'll do 4 practice problems.